Exploration 2.4. We're just going to go through most of this together, and it's your job to follow along and get it filled out and do the stuff, basically. There's an Excel file for this. It's available on Canvas, so you should open that up and try to replicate some stuff in Excel, have some computations get done, and I will do those on the screen as well. But standardized ratios is the name of this exploration. We're talking about ratios, and a standardized ratio is a ratio where the second number in a collection of ratios is always the same, and it gives us a good way to compare some things. To start, here's three different ratios of pounds of brisket to people. And so these are like restaurant recommendations. How much should I get per person, basically? Well, restaurant A says get 2 pounds for every three people, and then we get some different sort of ratios for B and for C. And the question here is which one actually gives you the most brisket per person? Now, you might be able to solve that problem by just getting out your calculator and punching some things out, and we'll talk about that. But the point is, these are hard to compare because we have different pounds of brisket for different size groups of people, so it's not immediately obvious which one actually corresponds to the most brisket per person. The ratios have different second numbers in them. Now, ratios that have same number are called standardized ratios, and there are lots of those that we actually use. One of those are percentages, in fact. So the four that we're going to run into here are these. A unit ratio, so that's just something where it's some amount of whatever per single unit of something else. Percentages are standardized ratios using 100 as the second number. And the next two just basically tell you what the second number is in their name. Number per 100,000 or parts per billion. Those are also types of ratios that use the same number as the second number. And the point of standardized ratios is that it makes things easier to compare. These sort of non-standard ratios with different second numbers make things hard to compare. Standardized ratios, but make it easier on the other hand. All right, so to just start things off without even context, we're just going to look at these fractions. So there's the fractions from the barbecue restaurants, 2/3, or the ratios technically, the top being pounds of brisket, the bottom being people. So if these all had the same denominator, the same bottom number, they would be easier to compare, and you would know how big each one is relative to the others. And that's something that we handle when we add and subtract fractions all the time. We make common denominators, and if we could just do that, we could compare these more easily. And so it turns out with 3, 5, and 7, the smallest common denominator you can make is actually 3 times 5 times 7, which is 105. So we're going to convert all three of those fractions to have the same denominator of 105. And basically, to do that, you're just going to have, since we've got three fractions, you need to multiply the top and the bottom of each fraction by the two denominators that are missing. So for example, 2/3 is missing, well, it's got the 3 on the bottom. It basically needs a factor of 5 and 7. So I'm going to multiply by both 5 and 7, top and bottom, which means I'm multiplying by 35. And when you do that, 2/3 is the same as 70 over 105. So if you want to pause and give those other ones a try, that would make some sense. For 3/5, what are you going to multiply by, top and bottom in this case? All right, it's got the 5 on the bottom. It needs a factor of 3 and 7. So in other words, we're going to multiply by 21. That works out to this. And the last one, we've got the 7, so we need a 3 and a 5, which means we're going to multiply by 15, top and bottom, and that gives you this. So now you've got those three fractions, those three ratios, all with the same denominator. If we were thinking barbecue, this 2 pounds of brisket for 3 people is the same as 70 pounds of brisket for 105 people. But now they're all stated with the same number on the bottom, and we can compare them. And so clearly, 70, 63, and 60, this ratio has the most brisket per person. 70 pounds for every 105 people versus 63 and 60. So yeah, of those original fractions, 2/3. Now the other way you could go after this, and maybe this was your first instinct too, is just get out your calculator and punch them out as decimals. All right, so we're going to do that to the nearest thousandth, so 3 digits after the decimal point. So round them if you need to, or add zeros if you need to. And so compute 2/3, 3/5, 4/7. All right, end results. Now we know this one should be coming out bigger. We already saw that it should be bigger, and it does. And when you write out those decimals, they look like this. And those are terminated and rounded, except for this one, which is actually just 0.6. So we add a couple zeros on to get to the thousandth place. And another way to think of decimal expansions, when we chop them off at a certain spot, if we end after 3 digits and round it, this number, this is thousandths, 667 thousandths, meaning this terminated decimal is the same as saying 667 over 1,000. So you could also interpret these approximations, these decimal approximations, as ratios. 0.571 is 571 over 1,000, for example. All right, to real quick do number 2, and then we'll get to Excel. The word per shows up in lots of ratios. We were just talking about pounds of brisket per person, for example. And if you look up the word per, you can get some longer definitions, but really the most straightforward definition is just for each. When we say per, when we say 2 pounds of brisket per person, we're saying this ratio is 2 pounds of, well, yeah, 2 pounds of brisket per every 3 people, for each 3 people, and so on. Or 2/3 pound per person, for each person. So if you were to take, if your car got 29 miles per gallon, as it's usually stated, if you were to write that without using the word per and describe what that means to somebody, it would be something like this. So for each or for every, that's similar language. This car can travel 29 miles for every gallon of gas. Okay. On to the next page, and we will get into the Excel stuff. So Excel 2.4, which I will now put on the screen. That has 4 tabs. We're going to go to life cereal prices here first. All right. So you'll have to kind of, I'm going to leave Excel on the screen, but follow along on page 73 here. All right, so you go to the store and you're looking at 3 different size boxes of Life. One, this literally, if you look, they go to the store and find these. One doesn't really have a name, but they have a family size box and they have a giant size box. And here are the prices that I found, and here's how big each box is in terms of ounces. So this is a common grocery shopping question of which one is the better deal. And sometimes it's the larger one, not always, not for everything. So sometimes these computations are good to think about. Now in Excel, there's just 3 little computations here, but we would like to know, given the different sizes here, how much are we paying per ounce in the end? All right, so we're just going to tell Excel to take the price for that first one and divide by how many ounces it is. And there we go, formatted in dollars already, about 29 cents per ounce for the regular size box of Life. And we're just going to have it do the computation here too. And we'll get that by just playing copy and paste. And ooh, you can see family and giant come out pretty close to the same. 0.24. So which one, now that's essentially, they're the same deal. Not a huge difference money-wise. But to technically answer the question, we need more digits. So this is rounded to the nearest cent. Up here in the middle on Excel are these two buttons where you can adjust how far or where the decimals end, or yeah, so you can make it add more decimals or take away more decimals. And so for both of these, I am going to extend it out. Oop, and even if we go another one, it's still the same. And if we go another, there we go. And the giant box just barely wins for cheapest per ounce. So on Excel, just to answer some questions, I'll actually go back to it now. Yeah, what are the ratios that we're making? Well, the point is we're making a unit ratio. We're computing dollars per ounce. And my fussy little dog behind me can't get up on the bed because there's something in the way. So I'm going to move my binder. Okay, there we go. All right. Back to this. We're taking these different prices that correspond to different size boxes and turning those into ratios of dollars per single ounce. And that way we can compare these prices and see which one is really a better deal. So we're making a ratio with a 1 on the bottom, in particular 1 ounce per cereal. So in cell D2, no, D2? Oh, I moved it. That should be E2 now. We're going to change that. E2. We got 0.29. We got 29 cents right there. So this is saying, yes, the price of this 13-ounce box of this regular size box of Life is equivalent to paying 29 cents for each ounce of the cereal. And it turns out the other two sizes are a better deal. It's closer to 24 cents per ounce. And who's a better deal? Well, yeah, this is what we saw. Just barely the giant size is better than the family size. But then if one of them goes on sale, that makes it an even better deal, and then maybe that's the one to buy. And sometimes small sizes go on sale and they're still not as good a deal as bigger sizes. So anyway, it can get tricky. All right, in the next tab, wow. NBA win totals. I have, oops, there we go. A few NBA teams, not all 30 of them. And these are their historical stats up to a certain year, how many games they played and how many games they've won. And you can see different numbers of games for different franchises because some go way back and some don't. And we're just going to compute the win percentage. What percentage of the games they played did they actually win? All right, well, that's an easy computation. It's just wins divided by games played. So we can just say, for the Pistons here, C2 divided by B2. All right, we get this decimal now. It is not formatted as a percentage. So if we were going to state it as a percentage, we would need to move the decimal point over a couple spots. But rather than actually making it do that or multiplying by 100, we can actually just go right up here and click the percentage button and it will change the formatting to a percentage. And there it is, 48. Now I'm going to go one decimal further. So we see it's rounded to 48% for the Pistons. And if we tell Excel to add another decimal spot, it does another decimal place, it's actually 48.2. All right. So before I copy and do the rest of those guys, which will take no time at all. What is this saying? Okay, well, we're making a percentage, and the whole point of a percentage is that it's a portion out of 100. So we're taking all these different teams with completely different numbers of games played, and we're scaling them all and basically looking at, on average, out of 100 games, how many have they won? And for the Pistons, it's right around 48. So even though they've played 5,700 plus games, and they've won almost 2,800 of them, if we scale that down to make things comparable, with these other teams that haven't played as many games or haven't played the exact same number of games, we can say this. 40, yeah, well, make this statement right here. So that word percent, yeah, if you know some Spanish, it might make some sense where that comes from. But the word percent is very much related to the hundred. So the per, like we talked about before, is like translated for each, and cent is that prefix that means, or suffix that means 100. So when we're stating a percent, we're saying this many for each 100 whatever. The Pistons have 48 wins for each 100 games they play. All right, so who's doing the best here? Well, if we copy that down, and look at those numbers. Highest winning percentage, just barely, the Spurs beat out the Lakers. Now, the question in the exploration is which team has had the most success? Now, if we just defined have had success as winning the greatest portion of their games, then the Spurs win. If you know NBA history, the Lakers are older, they've won more titles and that sort of thing too. But if we just look at this, the Spurs win by just a smidge over the Lakers. The Celtics are a little behind them. And the worst, oh my goodness, I'm realizing when I wrote up my notes that I wrote the wrong thing. The Memphis is not great here, but the Clippers, Los Angeles Clippers, are even worse. So actually going to here, I had, whoop. Oh, no. Okay. I did say the right thing. I just wasn't even noticing we had one that was below 40. Minnesota is under 40% of the games that they've won. About 39%. So they have the lowest one. Not those other two. Okay. Moving on. Third one. Homicide rates. Less happy topic. These sort of statistics for states, cities, crime stats in particular are often stated like this. Birth rates are often stated this way too. Obviously, different states have different size populations. So if you're trying to compare crime statistics, it doesn't make sense to just count how many of something happened because Texas has a much higher population than Kentucky. So you're going to get more of pretty much every type of crime in Texas. But the question is, we want to scale that down to the size or based on the size populations for those states. So the way we do that, so these are numbers from 2019. Also, since you wouldn't go about and say what percentage of the residents were killed, mostly because that's a really, really small percent, and you don't want to measure things with tiny, tiny numbers. So instead, how they come up with homicide rates is that they use the number 100,000. So imagine you take your entire state population and you divide it into groups of 100,000. And then you can say, okay, for every single group, on average, how many homicides are there? So in that first slot for Michigan, the 5.57, what does that mean? Oh, so first off, this is the one for Alabama. B4 is Alabama's homicide rate. If you just write the ratio that you get, it's saying there are a ratio of 7.3 homicides for every 100,000 residents. So if you took Alabama's population, divided it into groups of 100,000, and then divided all the homicides by however many groups, this would tell you on average how many homicides there were for every group of 100,000 people. All right. So the second number, in all of these pieces of data for the states, they're all ratios comparing something to 100,000 people. And that Michigan number, if we were to write it out in words, looks like this. Homicides in Michigan in 2019, they average out to that number, 5.57 homicides for every 100,000 residents. All right, again, a percentage doesn't do a lot of good here because percentages would just be too small. All right. If you were to ask what percentage of the people were killed in a homicide, you would get a very, very small percentage, 0.0000 something. And those numbers are just so small, it's ridiculous to work with them. So instead, we compare it to groups of 100,000, and then we get reasonable sized numbers like 7 and 5 and 6 and 4 and stuff like that. Okay, so answering these next questions, highest and lowest homicides, well, you're just looking, or not the totals, but rate. You're just looking at those numbers in column B. Which one's biggest and which one's smallest? Well, of those 5, Ohio has the lowest because that's 4.6 is the lowest number in that column. And Alabama has the highest with that 7.3. Mathematically, what we're going to do here is have Excel tell us now how many homicides there were. We're going to use these numbers to actually figure it out. Now, you would expect that Texas is going to have the most because its population is by far the biggest, even though its rate is not as high as Alabama's. Since it's got so many more people, there are probably going to be more homicides in Texas than anywhere else. So here's how we do this calculation. So remember, this is how many homicides per 100,000 people. So first we're going to have Excel. Not right there. Right here. It's going to take the state population, which is almost 10 million for Michigan, and we're going to have it figure out how many groups of 100,000 you get. So we're going to say divided by 100,000. There we go. So if we just had Excel do that computation, that would tell us how many groups of 100,000 there are in Michigan. But then we're going to multiply by how many homicides there are for each group. All right, so this division tells us how many groups of 100,000. Now we need to multiply by how many homicides per group. And so if we enter that, we will get our actual number. So 556. Now, of 0.27, there's some rounding here in some of the things, and obviously we can't have a quarter of a homicide. So I'm just going to tell Excel to trim off those digits. So I'm going to use my digit adjuster here to take away decimal places. So we're just right there at a nice whole number. All right, so that's the basic formula. We can just copy it down then to the other ones and see what happens. And unsurprisingly, Texas had the most, but Texas had the most people as well. So that's not very surprising. And Kentucky had the least. That's all that we need to point out for that last question on page 75. All right. One more, and there's no Excel computations to do on this one. We are just going to look at the data. So this is actual lead content in the drinking water data. The unit for these numbers, though, is ppb. That is parts per billion. So lead in the water is bad, causes birth defects and brain damage and all kinds of bad stuff. But there's really such a small amount of lead actually in water that you wouldn't want to say what percent of this gallon of water is lead. It would be an incredibly tiny percentage, even tinier than the ones we were just talking about with homicide rates. So the way they go then is to think about taking any sample of water and chopping it into 1 billion pieces and then counting how many of those pieces are lead. All right. So on my notes here, I actually switched 2 answers because I wasn't paying attention enough. In the exploration, question B to start, what is the second number in these ratios? Well, it's parts per billion. It's billions. All right. All right. So letter A, write the piece of data in B2. So that was right here. Troy, Michigan, they had a lead content of 1.1 parts per billion. All right. So if we were to measure the water by weight, say like in milligrams, which is what is measured or what is mentioned in the exploration. Again, I wrote wrong thing in the wrong place. I didn't want to rewrite everything. This is what should be up in A. So just writing the ratio, 1.1 parts per billion means for every billion milligrams of water, there's 1.1 milligrams of lead in it. That's just the straight up ratio. Now, interpreting that, and that's what's asked in letter C, but I wrote the answer up in A. So in B2, what does this mean? So the water in Troy, for every billion milligrams of water, you would have 1.1 milligram of lead. All right. So this gives us a way to compare the lead content in different cities. They have a method of taking a sample of water and they measure, in some quantity, how much of it is lead and can turn that into this, the ratios that we have here. So lowest lead content, well, we got a nice fat 0 right there for Big Rapids. Highest is clearly Flint, and that was the problem. 27 is a huge amount of lead. Still parts per billion. So most of your water is water, but there's still enough lead in the water that it's bad. So the rest of these questions get at these different thresholds. So different organizations would have different opinions on what the bad amount of lead is or what's some sort of lead level to be worried about. And the EPA, the United States Environmental Protection Agency, that says 15 parts per billion is bad. And out of all of these guys, only Flint is above 27. But if you go down to 10 parts per billion, which is a World Health Organization threshold, then they say 10 parts per billion, and now we've got both Flint and Kalamazoo meeting that threshold. And if 5 is cause for concern, well, now we actually get Muskegon in the mix as well. All right, so yeah, there's 2.4. There's a couple questions on the next page, but we're just going to leave those as they are, and that will do it.